Good evening, ladies and gentlemen. I'm Anne Greenoff, and I'm Head of School of Medicine here at King's College London, and I would like to offer you a very warm welcome to this inaugural lecture. Inaugural lectures are to celebrate such excellence in academic achievement that KCL promotes an individual to a chair. Tonight we're here to celebrate Professor Provost's academic excellence. He graduated from the University of Southampton with a first-class honours degree in a BSc in mathematics with statistics. He then completed an MSc in statistics with applications in medicine with distinction. He then took his PhD in social statistics and then a series of posts at the University of Cambridge, including immediately prior to coming to KCL, being head of the Statistics and Modelling Group with the General Practice and Primary Care Research Unit. There, Professor Provost was responsible for delivering statistical input into a number of trials of complex interventions targeting changes in lifestyle behaviours to physical activity, smoking and diet to prevent obesity. He was appointed reader in medical statistics at King's College London in 2009, when he has particularly focused on randomised trials in those important areas. I am delighted then to ask Professor Provost to give his inaugural lecture entitled Statistics in Trials, Making Complexity Work. Professor Provost.
Thank you very much, Anne, and thank you everybody for coming. But don't go just yet, because I want to tell you a story. Okay. It was Benjamin Franklin who said, "Believe none of what you hear and half of what you see." And these are very wise words. These are the words that a headmaster of mine told me between moving schools. And I didn't really understand it at the time, but now that I'm a bit older, I realise that we have to take very seriously what we see and hear, take it with a pinch of salt, and be very, very careful to not believe everything we hear and see. And often what we do hear and see is accompanied by numbers and statistics. And there's another saying that I'm sure many of you are familiar with. By the way, don't apply this particular phrase until after this evening, because then you'll believe everything I tell you. There are three kinds of lies: lies, damned lies, and statistics. That was popularised by Mark Twain, and he thought it was first said by Benjamin Disraeli, a Prime Minister in the 19th century in England. And statistics, for the defence of statistics, I would say that there are two kinds of statistics. Statistics that are the numbers that we see around us that can be used can be misused and can misrepresent what we want them to, what we intend them to represent. And then there's the capital S, the subject statistics, and the two are quite different. Statisticians themselves often get involved in two major activities. These are developing statistical methods and applying them to provide statistics, hopefully the right kind of statistics. And statistics comes into the fore when we ask questions of the wider population. We might have a particular question like, what's the prevalence of diabetes in the UK? And that might set us on a research study. And the research question that we want to answer in the population, we answer in a small fraction of the population called the study sample. So statistics is all about trying to make calculations within the samples amongst a fraction of the individuals in the population so that we can make inferences or conclusions about the wider population. So we calculate sample statistics such as the proportion of the sample that are found to be with obesity, and then we hope that this is an accurate estimate of what we want to estimate in the population, the prevalence of obesity. My first post was with the Health and Lifestyle Survey. I'm very pleased to see Brian Cox and Margaret Witchlow here in the audience today, the director and another researcher on the survey. It was a survey of 9,000 individuals all round Britain, and it was done in the mid-1980s, and adults of all ages. And this was a very big enterprise because it involved interviewers coming into your home if you were a particular participant of the survey, and followed up with a nurse visit taking all sorts of measurements, and then a questionnaire was left with you so that you could fill in yet more information about yourself. And the sorts of information that were collected by these three means were your beliefs about health, what sort of lifestyle factors you're involved in, smoking, diet, physical activity, and also the health conditions that you might self-report within the survey. And the nurse collected lots of measurements such as weights and heights and lung functions, blood pressures and so forth. And statisticians are often concerned about missing data, and there were a couple of respondents near my hometown in Rochford, and the director asked me, could I be the nurse for them and take their measurements? And being a statistician, I thought, well, yes, I think I will do that. So I know quite a bit about lung function and blood pressure by that. Now, these days, I don't think you could get away with that because you have to go through certain hoops to be able to do that, but I won't mention that any further. Okay. And we've got a lot of psychology and psychiatry information as well from the questionnaire. So a vast amount of information on really a vast amount of individuals. So a very rich source of data to answer many research questions. Also, the director and other researchers linked every individual in the survey over time so that any incident cases of cancer or their demise were actually recorded so that any particular aspect in the survey could be related to later mortality. And then another great enterprise began in 1991. They got funding to be able to resurvey the people, and just under 6,000 of those surviving were resurveyed, and again, the similar information was collected, and this allowed even more powerful questions to be answered. Have people changed over time? One of the very interesting parts of the questionnaire was to try and get the people to show whether they had good reasoning or poor reasoning, and the block counting test was a fascinating test where you have to try and imagine how many blocks there are in each pile. And I can see you're all having a go at number one. I'm not going to give you very long, so you better hurry up. I think number 4 is the hardest, by the way. But a very interesting thing that they found by the time of the second survey was that in the first survey they saw that reasoning seemed to decline with age. But because they had the second survey available, they were able to find out that it is actually us as we get older that it is the factor that is connected with our decline in reasoning, not that different generations might have different abilities. But our question today is more about obesity. And obesity is defined in a number of ways. A very common definition is that you have a body mass index over 30 kilograms per meter squared. So it involves your weight and your height. And here are some examples of weights that would be applicable, above which you would be defined as being obese. And central obesity, such as waist measures relative to your hip or height, are also important for outcomes later in life, health outcomes. And from the survey, they found that just under 10% of men and about 15% of women were defined to be obese in 1985. I think you can see where this might be going. Okay. On the resurvey, the percentages have gone up to 15% and 20%. And from this point onwards, we refer to the Health Survey for England, a series of surveys done annually. And if we average each set of 3 years, we get more robust estimates, you have to believe me. And everything looks much smoother when we do this. And if we look at men, we can see that the proportion who are obese has increased quite steadily and quite dramatically to nearly 25% of the population. And for women, again, just over 25% quite recently. So about a quarter of the population in the UK, or in England in this particular survey, are defined to be obese. So it matters because it can impact severely on an individual's health all sorts of conditions such as some cancers, liver disease, heart disease, and type 2 diabetes are all consequences or very highly related to obesity. And your risk of these diseases increases as you approach obesity and become obese. It's also a so-called burden on the NHS to have to treat the condition and the consequences. So we're going to focus today on type 2 diabetes because a number of people that I've worked with have had a keen interest in that particular condition. So obesity is a major influence on type 2 diabetes. We can, thanks to the MRC Epidemiology Unit in Cambridge, they provided me with some useful maps so we can get an insight as to where diabetes is highest, and the darker shades indicate that perhaps there might be 10 or 12 or more % obesity in those particular countries. And you can see it's largely a condition of the more developed countries. And if you look at the map closely, we're going to move on 20 years, you'll see that there's a change, and it's in the upward direction. We're expecting perhaps 1, 2, or 3% more prevalence of diabetes over the next 20 years, perhaps as a consequence of lifestyle factors and obesity itself. If we focus in on England and the UK, that's that little country in this great big world, you can see that it perhaps has a lower prevalence of diabetes than America, for example. And although the MRC Epidemiology provided me with these maps, I must make the excuse that I'm not very good with PowerPoint in terms of colours, and so England might sort of fall into the Atlantic with this particular colour, but I think actually it does, you can actually see it, so that's a relief. Okay, and you can see that broadly speaking, only about, we have a prevalence of about 7 or 8% for diabetes in much of the country. But as you look at the map and move through 10 years on, we're moving up 1 or 2%. 10 years further on, and we're moving up to quite a lot of areas with 10% of their population having diabetes. So again, this is a growing problem for the world and also for our country as well. And okay, so what influences obesity itself? Well, lifestyle factors are the sort of main determinant of obesity, but obviously genetic factors could play a part, but that wouldn't explain the rise in obesity over the period of 1980s through to current day. And what sort of lifestyle behaviours are we talking about? We're talking about high energy dense diets, and we're talking about smoking having an impact on type 2 diabetes and its consequences, heart disease, and physical activity or sedentary living, where we're not doing as much activity perhaps as people our age a generation earlier. So we're going to go through these three lifestyle factors as part of this talk. We're going to focus on diet first, and the burning questions that we might have had in the 1980s were, what is the British diet? How can we measure diet? And how healthy is the British diet? And many of these questions are valid today. Statisticians often talk in terms of frequencies and how much and what did you do last week and next week. And so the statistician's view of diet depicted in this cartoon, in order to choose what you're going to have for your sandwiches today, you find out what are the most popular and least popular items that people choose for sandwiches. And so I think this is quite funny, and you didn't laugh, but never mind. I should have given you the signal. Okay, but actually this is quite an interesting cartoon because the most popular and least popular items is a very relevant phrase, because in the Health and Lifestyle Survey, that was exactly what was asked of people. How frequently do you eat fruit in summer, fruit in winter, salads and meat and vegetables and nuts and chocolates and things like that? And this is known as a food frequency questionnaire because we ask people about the frequency with which they eat these foods. This is commonly used in very large studies because we can't afford to take the time to persuade people to weigh everything that they eat when we have such a large-scale survey. Previous research focused on one food at a time. So what's the impact of processed meat on cancer, for example? But our food choices are more complex than examining one item at a time. And with these 39 food items that were recorded in the Health and Lifestyle Survey questionnaire, we can realise that people do make correlated choices when we go shopping. We buy a whole series of food that we're planning to eat together. We don't focus on one food at a time. And so we have this sort of problem that we have all these dimensions of 39 possible different foods that people might choose to have, and we might want to try and disentangle what's the effect of one food when we control for all the others. But this is perhaps a fallacy, because in a way we eat food in patterns, in dietary patterns. And with so many foods, we have quite a high dimensional problem to try and find out what is the British diet. So the research questions that we have are, can we deal with the complexity and find what are the British dietary patterns? How healthy are these? And it was Carl Pearson back in 1901 who came up with a particular method of principal components. And in his paper, he mentioned two particular variables. One was people's height, and one was people's leg length. You know, if I took all of you and asked you to come down to the front and lined you up from the shortest to the very tallest, and then I asked you to measure all your leg lengths from the floor to your hip, then you would come up with a value. And if I shuffled you all up and ordered you now according to your leg length, you'd probably be in pretty much the same position that you were originally. So basically, leg length and height pretty much tell you the same information about your relative standing amongst your peers. And so Carl Pearson said, well, we've got these two complicated dimensions. Wouldn't it be nice if we could simplify everything to one dimension? And he said, well, if we've got height, we don't really need leg length because we can predict leg length from height. We could just halve it, and that'd be about right. And we could go the other way. If we've got leg length, we could double it. And we've got height, we only need one of them. And then he came up with this method that was a bit better than both of those particular scenarios. He said, well, let's think of a line of best fit that we could put through the points. And if we put this line of best fit through the points, we might retain even more information than if we only looked at one of those things individually, height and leg length. And this was known as the principal component, and it retains as much of the variation as you get from one edge of the data to the other edge of the data. If you place any other line through that data, the bit that hits the points will be quite short unless you do that particular line that stretches out with maximum variation there. So one way of thinking of it is that you're retaining as much variation or information as you can with this particular line. And Carl Pearson tells you how you can find what that line is. Another way of thinking about it is in terms of something called correlation. How close are those points to the line that you might put through the data? If you put the line through the data through the line of best fit, then those points are the closest to the line as they possibly can be. Any other line, you get points that are not terribly close. So variation is the opposite, the other side of the coin of correlation. And if we can do this, then we can reduce the problem down to one simple dimension. And it might be that we take a third of your height and 2/3 of your leg length times 2, and that might give us the line of best fit, which would retain the correct order were we to think of you in these two dimensions. Of course, Pearson could have measured arm span as well, which would be another measure which might be very correlated with your height and your leg length. This time, we'd be in 3 dimensions. So instead of having a cloud of points like this, we'd have to have a third dimension of arm span coming out. And so all these points would probably come out at you like this, and we'd be fitting a line through the 3 dimensions. And if it was as closely packed as these, we'd be very pleased because we could summarize all that information with one line involving a combination of those 3 things, and be very happy because we'd be able to analyze all our data with very simple methods, only having to look at one particular combination. So it's a method to simplify what we observe, and what we observe is complexity because we have so many dimensions. Health and Lifestyle Survey, we have 39 of these foods. We can't imagine 39 dimensions, but the method, amazingly, can still be used. So the method uses everybody's correlated choices to find a strong pattern, a combination of those items. And so we start off with the 39 items in the food frequency questionnaire. We ask everybody, how frequently do you eat each item? And we translate this into a score for each of the foods, which mathematicians often like to use things like X and Y. So we've got X1 to X39 there. And then we get our combination, a weighted average of those original items. So weighted average, it might have been of height, leg length, and arm span, but in this particular case, it's all those 39 foods. And this gives us a principal component, and this is what Margaret Richlow and I found coming out from the Health and Lifestyle Survey data. Now, if you can actually get about 39 of those items out, 39 of those components out. There's the principal component, and other components come out if we go through all the dimensions. Because basically we're replacing the original items by components. But only 4 of the components turned out to be quite important relative to the noise that we see in the other 35 components. So these 35 components at the end are not terribly remarkably different from each other. This is a bit like the 39 steps. As we move up from one to the next item, there's not much change in how much is being explained by each of those very small items. But suddenly we find these 4 that are quite important that are reported in the paper. Today we're just going to focus on the first one. And that represents about 40% of the worth of those 4 items. So quite an appreciable proportion. Let's get an insight into how this method works then. Say that only 5 foods out of the 39 came out as being important. We could think of somebody in the room. I'm thinking of somebody in particular over there. He might eat quite an average amount of vegetables, average amount of fruit, average amount of salad, average amount of fried food, average amount of chips. And we can get a score for him by doing this weighted combination, and he'd be pretty average, get a score of 0. There's Mr. Average, okay. And we might move to the next person in the room, and this person, she eats a lot of fried food and chips, and is pretty average on vegetables, fruit, and salad. She gets a lower score of -1. This is because the weightings are positive for the top 3 items and negative for the bottom 2 items. We don't impose that, the data tells us that. And we come across another person who perhaps eats even less vegetables, fruit and salad than average, and still eating a lot of fried food and chips. They might get a score of -2. And then hopefully there might be someone in the room who's the opposite, who's eating a lot of vegetables, fruit and salad very frequently, and very infrequently eating fried food and chips. They get a score at the top end of the distribution too. And it so happened that when we went through everybody in the survey, all 9,000 of them, and looked at their scores, they looked very much like this curve. This curve is known as the normal distribution. A lot of people in the middle, a lot of average people, and quite a few around about the middle, but only a few people doing, if you like, very well, eating all the what we might call best foods, and only a few people eating the sort of the worst foods. And this happens quite a lot in nature. And it was Francis Galton who noticed that adult heights, when we line you up, if we draw a graph of you, a histogram of you, then it would turn out to be the normal distribution. And he got very excited about this, I can tell, because he made something called a bean machine. And Francis Galton's bean machine basically generated normally distributed data. And it's the first generator of normal random variables. And the way it works is that you have a pin at the very top, and then you have 2 pins underneath exactly symmetrically below, and then below every pin that you have 2 equally spaced. So it's a nice little game. You drop the balls from the top, and there's a 50-50 chance that they could go either way. And it's very unlikely that it would always go hit left, hit left, hit left, hit left. There's only one path that goes there. So very few people actually end up low in the distribution, and very few high, and a lot of people in the middle, because there are many paths to get that way. So, with all these foods that we had in the survey, what foods actually did come out as important? Well, it was fruit and salad. It was also fruit juice, vegetables, whether green, root vegetables or other vegetables, eating brown bread rather than white bread, eating low-fat bread, and having semi-skimmed or skimmed milk. If you ate those frequently, you get a much higher score. And if you ate these three foods, then that brought you down. So chips, processed meat, and fried food, you went down. So this was labelled a fruit and fibre dietary pattern, and it contrasted those particular things. And it represented about 10% of diet and about 40% of the non-noise part of diet. And interestingly, we were able to relate this score to other factors, and we found that women were more likely to be scoring high on this fruit and fibre diet, whereas men a bit lower. And women in non-manual occupation households were scoring higher than their manual counterparts. Similarly for men. And you can see the point differences are quite large. From the women non-manual to the men manual, those vertical differences are about 1 point, which is quite a shift in that distribution, that normal distribution, 1 point. Also, we noticed that the younger people in the survey were not scoring as highly as the middle-aged and older people. They were getting much lower scores than average. And perhaps this suggests that the generation then were not eating this particular pattern of diet and perhaps shifting away to other things. We also found that it's higher in the south and east of Britain and lower scores in the north and west. Smaller households tended to have higher scores, and non-smokers and ex-smokers also tended to have higher scores on this fruit and fibre dietary pattern. Low and moderate drinkers as well, and those who reported themselves to be in good health. So here was a pattern that really seemed to make sense and fit well with other lifestyle factors, and gave us an insight into diet, this perhaps multi-dimensional complex thing, which we've been able to reduce into something manageable that still represents a lot of the dietary information there in the questionnaire. We also found that the women who had the very high scores tended to have a 12% reduction in their mortality 7 years later for every half point of the score above their counterparts. And in a follow-up paper where we applied the method to the later cohort, we were able to look at change. And the change, we noticed that as people altered their smoking habits and gave up smoking, either reducing it or giving up altogether, they tended to improve on these dietary scores, the fruit and fibre score. So again, the change went hand in hand. And also, we noticed that the advantage of the non-manual occupations grew over the time of the survey as well, so a widening divide. And in a further cohort 3 years later in Cambridgeshire, we also found that this dietary pattern was associated with central obesity and undiagnosed diabetes. So that's diet, and what we've been doing is observational research. We've observed what people are eating, and we've learned quite a bit about it and associations between diet and other factors. Of course, what we'd quite like to do is to intervene so that people are enabled to change their lifestyle factors. And when we move over to smoking, we're going to look at intervention. So what have we learnt so far? Well, on the health side of things, we've seen that obesity is important in terms of its consequences of type 2 diabetes, and it itself is determined quite largely by lifestyle behaviours. So what we've done is all about applying existing research methods that Pearson developed 100 or so years ago, and using them to help us to advance our health research, use these tools in order to get a greater understanding through health research. And we do this so that we can improve health practice so that people know about these things and perhaps can develop interventions to try and change the situation. And these arrows work the other way as well, because when we are engaged in health practice, that often suggests particular research that's needed. And then we engage in health research, and then we go and select research methods and apply them in order to answer the question. Health research is done in several stages. you have an idea for research, and then you embody it within a research study. You design the study, you conduct the study, and then at the end you evaluate the results from the study. And what you really want is a good study sample, a sample that's going to be representative of the population. If we've got a sample that's representative of the population, then the answers we get from the sample are going to be trustworthy and tell us something about the population. We'd like one that has no tendency to lie, thinking back to our phrase that we had earlier. No tendency of bias. And we want a study sample that's reliably informative. We don't want one that's not going to tell us much. We want one that's going to be informative. And we want that to be informative, invariably so, all of the time as much as possible. And one of my grandparents used to tell off his children for getting confused between two words, same and similar, when they were comparing things. And same and similar are quite similar words, but they're not the same. And the meaning of same is not the same as the meaning of similar, but they are quite similar. And in the same way, or similarly, statisticians are taught about two words, accuracy and precision. If something's accurate, is it precise? If it's precise, is it accurate? It's very easy to get confused between the two. And so I'd like to share with you a particular way of thinking about accuracy and precision. So here's an example that we'd all love to be in this particular situation where we're very good at archery, especially the young people in the audience, I know. And if we're able to hit the target over and over again, we're both accurate and precise. And that would be very good news. No bias there at all. But on the other hand, we might be inaccurate. And there are three ways we can be inaccurate. We can be inaccurate by being precise but biased. So we're precise, we're hitting the same place over and over again, but we're getting it precisely wrong. So we've got bias there. So inaccurate. On the other hand, we might have no bias, but be imprecise and be a bit all over the place, but on average, we're pretty much okay. And that would be inaccurate. No bias there, no systematic, like the second example, but perhaps a bit of variability there. And the fourth way, you want to give up archery and take up another sport because you've got bias and variability or imprecision. We can cure the third one along from the right by taking a larger sample. If we aggregated all those arrows together into a much bigger arrow that was so they're less flimsy than the individual arrows, then when we shoot it, it will tend to hit the target and be rather like the one on the very right of the screen. So we can cure that by taking a larger sample size. But the one between those two, where we have bias, taking a larger sample doesn't improve the situation. We just end up hitting that spot. So bias, arguably, is more important to try and get right and improve. So for the worst situation, you've got to get a larger sample size and correct the bias. So bias is very important. And statisticians link these two together with an equation, as they often do. Inaccuracy depends on the bias and the imprecision. So the bigger the bias or the bigger the imprecision or variability, then the bigger your inaccuracy. So really you want both of those to be favourable. You can think of the arrow as a sample, a particular sample of people, and you're trying to be invariably on target and hit that bullseye, which is the population. And if you've got a representative sample and a big enough sample, then you're going to be in that favourable position on the right, and you're going to hit the bullseye and get really informative, accurate information. So how can we minimise the bias and get us back on the right track towards the bullseye? What stage should we do it at? Well, we're always encouraged as statisticians to tell everybody that you should do this at the design stage. Design stage, before the arrows are shot. You want to select the right bow, not one that's too big for you or too small for you. And that way we can eliminate some of the bias before we actually get on to taking the shot. So we want to design a study to be on target and have low variability. So those are the sorts of issues that you might come up with a statistician when you come to them and want to design a study. How can I eliminate biases, and how can I have a good sample size that will help me give informative information. So we can avoid bias at the design stage, and it was R.A. Fisher in 1938 who said to consult the statistician after an experiment is finished is often merely to ask him to conduct a postmortem examination. He can perhaps say what the experiment died of, but can't really help you. So, what can be done at the design stage? Well, one thing that we can do is to choose a good type of study design, which will help us minimize the bias. So we want to select the right bow. And if we're doing observational research, then we have some choices. One is the cohort study, such as the Health and Lifestyle Survey, where we select people and we track them over time prospectively to see whether particular events like cancers and mortality occurred. And this is quite a good design for observational studies because you're following people prospectively. You can get a lot of information about them at the beginning that's accurate, and you can then relate that to any future events. Of course, you might have to wait a long time, 2, 3, 4, 5 years to get the events, but on the other hand, it's well worth the investment. Another quick way of getting information is to use the case control study. Not such a good bow. Here we rely on retrospective information being reported. So we ask people who develop a particular disease, such as diabetes or cancer, what were you eating 10 years ago? And we ask a whole set of controls who haven't got diabetes the same question, and they can you can end up with distorted answers because you have to remember a long time ago what you were doing. And perhaps the cases remember better than the controls because they have the condition and had a good amount of time to think about it. That's known as recall bias. But both types of studies suffer from another bias called confounding bias. Now, we've seen earlier that for women, that diet was associated with later mortality. And that's quite interesting. But on the other hand, it may be that there's another factor, smoking. And if we look at this factor against diet, it might be that those who are eating low scores on the diet tend to have more smokers in, and those with high scores on the diet, favourably, might have a smaller amount of smokers in. And so there might be a link between smoking and diet. And we all know that smoking is associated with mortality, and because this other link comes in there, smoking is known as a confounding variable. And we might have confounding bias if we don't allow for it. We might blame a whole host of things on diet that may actually be attributable to smoking or vice versa. So observational studies have some drawbacks, but they're very good for answering observational questions and collecting very rich data sources to suggest new hypotheses for interventions, as well as confirm associations that might be known elsewhere. On the other hand, if we're in a situation of an experimental study, we might be trying to intervene on people to try and encourage them to change their diet or give up smoking or alter their physical activity. Then we'll be in the situation of this type of study, trials, and they fall into many types, but 3 common types. And 2 of them are the uncontrolled before and after study, where you measure something before, you intervene in the middle, and then you measure in the same people at the end, and you see if there's been a change. And there may well be a change in the direction that you hope for, but on the other hand, we haven't got a control group, it's uncontrolled, and so we never know what would have happened to these people had they not had the intervention. And in this case, this gives us perhaps low-quality evidence. We can find a better bow than that. And there are 2 other types of trials, the non-randomized controlled trial and the randomized controlled trial. The non-randomized controlled trial is where people are allocated to groups, but not at random. And the randomized controlled trial is where they're allocated at random. If it's allocated at random, then we get fair groups that are comparable at the beginning of a study. And that's good news, because if any differences emerge over time, then that can only be down to which group they were randomly allocated to, not to any other factors which would be evenly balanced between the arms. On the other hand, non-randomized control studies, you can think of a media campaign that occurs in Scotland, and it doesn't occur in Yorkshire, and all the individuals in Scotland are compared with all the individuals in Yorkshire to find whether there might be differences and changes in perhaps their lifestyles. That might not be a terribly good design. It's a non-randomized controlled trial, but we're in the situation where there are two types of differences. That they either got the media campaign or not, but also they were living in Yorkshire or Scotland, and there could be a number of other factors that might explain the differences that we see. And that's why the randomized controlled trial is the gold standard design, the best bow that we could hope for interventional studies. But Winston Churchill says, however beautiful the strategy, you should occasionally look at the results. So we can set off with a great design, but if you take your eye off the ball, it could be going all wrong as you conduct the study. And so even though you might have a gold standard randomized controlled design, if it's done poorly, then it's going to give low quality results. And so really we want to minimize biases not only at the design stage, we want to avoid them and evade them at the time that we're conducting the study and evaluating the study. We have to be mindful of the study types, choose the best one we can, be mindful of biases and try and avoid them in the design, and rigorously do the trial to standards that are accepted and useful, and also use appropriate methods when we evaluate the results so that we don't miss something by using an inferior method. So bias essentially, I think, mainly arises from poor choices that are avoidable, some are not, but they affect the conclusions. So for smoking, we start with our eligible population of individuals who might be smokers in this particular instance, and we'd select a sample from the population in order to intervene and offer them an intervention to give up smoking. And generally, with a randomized trial, after consenting the people into the trial and recruiting them and randomly allocating them, we follow these two groups up over time to see whether they quit smoking, what proportion quit. And so we follow them up. We calculate relative statistics, like how many more of the intervention group gave up smoking compared to the comparison group. And that gives us an estimate of what this might be in the population. Also, from the sample, we get a window into the population. Whenever we calculate something in the sample, we can put something called a confidence interval around it. And that's our degree of confidence as to where the true underlying particular value might be. And so the confidence interval is another measure that we have available that gives us an idea of what it might be in the population. Because each sample you take is a sample of different individuals. When we calculated our statistics on one sample, we get a different answer than if you calculated on another set of individuals. And so this confidence interval gives us a range with which we can be confident that the answer might lie. And the particular interventions that were of interest to Felix Norton and Stephen Sutton in Cambridge were known as self-help smoking cessation interventions in the period of pregnancy. And these self-help interventions, by their name, it's all about helping yourself to give up smoking. So you're provided with structured materials, booklets, perhaps text messaging even, that assist the individual to quit smoking. And their focus was on the period of pregnancy, and they trawled through the literature in a very systematic way and found 12 trials that had examined this question. And what we would really like to do is not just look at one study in isolation, but aggregate all the information that we can from those 12 studies to get a bigger picture of what's going on in the population. Each of those studies has a degree of confidence, and we want to harness all the information from those 12 studies and get a more precise picture of what the population effect might be. So how can we maximize information? Well, each of these 12 studies have gone through the process that we mentioned before, and we can pool these research studies times 12, and if we do that, we're doing something called meta-analysis, another statistical method. And it's all about the bullseye again. So these 12 studies provided information. The very first study was done in 1985 and suggested that you're 7 times more likely to quit if you have this intervention than if you don't. That sounds quite useful. But the lines either side of the 7 show that we've got a lot of uncertainty. Could be nearly as low as 1.5, could be as high as 20. It's a very small study. It doesn't give us a lot of information, but the best estimate so far will be 7. And the next study gives us a value of 3. You're 3 times more likely to quit if you have this intervention. And we're getting some information here. And we can do the same for all the other studies. And we get information from every one of them as to how strong the effect is of having the intervention. And we end up with massive arrows. Now, whenever we do a study, it turns out we don't know where the bullseye is, but we shoot our arrow and we hope that it'll be somewhere near the unknown bullseye. So, in reality, we don't know where the bullseye is. All we see is the massive arrows, all the samples having a go at it. And what we want to do is try and combine all that information into a massive, great big arrow that will point to where the bullseye might well be. And that's what meta-analysis does. And at the very bottom of the plot, you'll see something extra, a diamond. This represents our best estimate of what the underlying effect might be. And it's around about 2. It's positioned around about 2 at the wide bit of the diamond. And where you hit the edges is your 95% confidence interval. So it's the interval where you're 95% confident the underlying true rate lies. So our best guess is around 2 or 1.83. And it could be anything from 1.23 to 2.73. So we've learnt quite a lot from all these very small studies, so that we have pulled all the information and actually learnt that this particular intervention is valuable. It does provide us with the means of giving up smoking. Okay. There's one very peculiar study there. You may have noticed, if you're an eagle-eyed person familiar with this method, the Moore study, it actually included a lot of people who had already given up smoking at the beginning, ex-smokers. So how could they give up smoking? So the effect is quite weak in that study. And we asked the authors, can you give us the information on those that were smoking at the beginning? But unfortunately, they did not provide us with the information. But it's always worth asking. So, from these 12 studies, we want to know what is the effect underlying all these studies, what's generated all these results, what's underlying, what is the bullseye. And if we do the plot another way, I forgot to say on the previous slide that the studies with bigger information get plotted with bigger squares. So you find that if we plot them, the information they provide against how successful they were, and you tend to get this sort of funnel shape. And you can see that there's a study here that seems to be at the top of possibly a funnel here. Bigger studies tend to be quite central to where the underlying effect might be, because they're big studies and big arrows tend to get near the bullseye, less imprecision, whereas smaller studies down here tend to spray out. So you tend to get sort of central study and then other studies spraying out like that. And that's the pattern we saw with 2 exceptions. One, this Moore study, which probably should have had a bigger effect if we excluded the ex-smokers, and would have been smaller as well by that exclusion. And secondly, we might call that selection bias. And secondly, there's evidence that there might be some missing studies, because normally we expect a symmetrical shape with not only studies on the right side of the plot at the bottom, we expect studies on the left side of the plot as well. We expect a bit of symmetry. But sometimes when studies are quite small and they give quite uninteresting results, they tend not to be written up by the investigators and don't get into publication, or they may be written up but they're not accepted by a journal. And so sometimes you see this gap at the bottom of the plot. And so perhaps there's a bit of bias in this particular analysis. But if we shift that study to the right and put in a few studies on the left, we'll probably end up with about the same answer. It's actually very hard to quit smoking. In the control groups of all these studies that didn't get the intervention, only about 5% of people were able to quit. And I find that quite amazing, because all these people are motivated to go into research study and they're not able to quit. And doubling the rate to 10% is very valuable, although it wasn't the doubling that I would have hoped for. Perhaps 20% to 40% would have been great. Okay, we're moving on to physical activity now. So what have we seen so far? We've seen that health practice governs often what health research we do because of gaps and needs. And we've seen that we need to apply research methods to be able to engage in health research. Similarly, sometimes methods aren't available, so we have to develop research methods in order to put them in the toolbox of applied research methods that people can use in their health research to answer health questions. So we're going to focus on one trial in this section. This is the proactive trial done in the General Practice Unit at Cambridge, and in collaboration with the MRC Epidemiology Unit and Biostatistics Unit. So it's a gold standard design, a randomized controlled trial. The intervention was all about encouraging people to increase their physical activity. That was the outcome. And the population was a group of people who were at risk of developing diabetes. Now, this group was identified by them having a parent with diabetes, and that's often a good indicator, perhaps, of whether the offspring may also develop it. So it's a very worthwhile group to try and increase physical activity and avoid or delay in any future diabetes. So the intervention was what's called a complex intervention. We're all individuals and we're all different and we all react in different ways, so we need an intervention that's going to target what might work for us. So a complex intervention involves a number of components that will enable each of us to perhaps have a hit and be able to move to increase our physical activity. So there's a number of plausibly important components, and they may act on their own or independently with each other, these particular components. And the team, before I joined it, did a lot of work at the beginning reviewing the evidence and the theory that backed the intervention. They developed a particular intervention based on what evidence there was about how successful a particular theory might be in changing people's behaviour. And after that, they developed the intervention with the help of the Royal College of General Practitioners, and then they tested the intervention in a pilot trial, a mini version, to check that everything was running okay. And then they moved on to do the main trial. And it's very common now to go through this process of being quite sure about the left side before you go on to do the main trial at the very end, so that you try and optimize everything you can and avoid mistakes that you could find earlier on, such as picking the wrong theory, forgetting to put a component in that's very active, and perhaps the pilot trial tells you that not many people are going to be recruited. So what was the theory that was used? Well, it's quite a common theory, the theory of planned behaviour. It's an observational theory. We collect information about each of you, and we collect 5 bits of information. Do you intend to do physical activity? What are your attitudes towards physical activity? What are the norms of people around you towards physical activity? And do you perceive that you've got control over doing that physical activity? And those 5 things are all linked together by arrows indicating how these things, if you like, hang together. So we can read off from this diagram that if we want to know about people's future behaviour, then 2 things that govern it are their intention and their perceived behavioural control. There's no link from attitude or subjective norm. Those 2 things are the proximal links, the close links to behaviour that are important according to this theory. And this particular theory guided how they built the intervention. Which components shall we put into the intervention? Let's put in the components that fit well with this theory. And they were quite meticulous, this group, and they collected lots of information about all these measures. They didn't just collect information about the physical activity at the end, they collected information about what they were doing at the beginning, their attitudes, and all the other variables that we've seen in the previous slide. They collected these via questionnaires, and this was a sort of psychological domain of the study, and then they collected information in other domains such as epidemiological, physical health, mental health, and certain conditions. So they put all these things together in a causal chain. They believed that if we could modify people's intentions, this might translate through all the way down to perhaps preventing diabetes or delaying diabetes. And they had many types of measures, questionnaires. People had to go on a treadmill to measure their activity, blood pressures and so forth. So they got to the trial, and they invited 53 practices to participate, and 20 general practices did participate. With 3,000 type 2 diabetes patients on their registers, they asked them the question, have you got any offspring that would be interested in participating in the study? They identified 1,500, and to cut a long story short, they ended up with 365 who were randomized into the study. Now, I said, to cut a long story short, there's a hell of a lot of effort to get through this process, to contact practices, get information from the practices about patients, contact the patients, get information from the patients about their offspring. They go and contact their offspring, and then the offspring say, I'm quite interested. You send them a questionnaire, and I could end up almost at the other end of the room with a number of processes involved here. And so there's a lot of work goes into these trials, and that's why they're so valuable, because they provide key information about the effectiveness of interventions. And the two trial coordinators, Kate Williams and Julie Grant, I can see in the audience, who are responsible for this particular process. And the target was to try and get 400 randomized, but we got 365, not quite up there. But a secondary target was to get 300 to be followed up by the end of the study. And that's really the more important target. And that's not because we didn't meet the first one. Okay. And I mentioned a couple of other coordinators from other trials as well, Fiona Whittles and Helen Morris. They put a lot of effort into these studies. And one of the things we did during the study was to track the recruitment. This can be a bit depressing because in many studies, it's very difficult to keep on track with the recruitment. You have a lot of optimism that the recruitment might be a certain trajectory as measured by the black arrow. So at every month we were going to recruit a certain number, but actually, as it turned out, we seemed to be on another trajectory that wasn't going to be quite good enough. And but somebody had a brainwave that we could not only recruit people through parents who suggest children, but we could also get at offspring directly. There may be people around who had a parent with diabetes, but the parent had died. And if we go through that route, we can get more people into the study. And so it took a long time to get ethical approval. You probably hear that quite often with research studies, but not always. And so it took a long time from that idea hitting to actually this engaging. And the novel recruitment took off, and we got on the right gradient, so things were looking up. And unfortunately, some of the intervention deliverers wanted to change jobs. And so we had all these people stacked up to get the intervention, and the facilitators that were left were too busy to take on. And so we had a very difficult situation. So these studies are very difficult to do, but they managed it, and they didn't delay anybody particularly long. And in the end, it turned out that 89% of the people at this particular point where we were reviewing the situation, 89% of them were followed up to 1 year, better than the 75%, 300 out of 400, that we thought. So the target of 400, we didn't need anymore. We could get away with a lower target. Okay, so we've looked at recruitment. In this particular trial, there were 3 arms. There was the comparison arm at the bottom, the control arm, who got a brief advice leaflet about physical activity. And then there were 2 intervention arms where the intervention was given to them, either face-to-face in person in their homes, or it was given largely by phone, the distance arm. And we can look at this another way. Of the 365 randomized, about 120 were in each group, and the intervention consisted of an introductory session where everybody is introduced to the study, and 4 core sessions. And they all got intermediate contacts as well, telephone calls, for example, or letters if they were in the distance arm. And after 6 months, we had measures to allow us to look at how they might have done at the 6-month point. And it also measures at the 1-year point, 1 year later. And at the 1-year point, we had over 100 there in each group. So we met the condition of requiring 300 after all. It actually turned out to be 91% follow-up. So again, a tribute to the trial coordination team. And the study was considered to be rigorously done because it was published in The Lancet. I think it was too. I think it was too. We all think The Lancet is great, don't we? Okay. And what are the principal results, though? These were a bit surprising. It turned out that everybody in all 3 arms, or not everybody, on average, they increased their physical activity, not just in the intervention arms, but also in the control arm. And when we look at the difference between the combined intervention arms, D plus F, this lot here, they had about a 20-minute extra physical activity per day on the flat, and this lot had about 22, 25 minutes extra physical activity. So the advice arm was slightly winning compared to the intervention arm. But perhaps a more interesting fact is that everybody did increase their physical activity over the period, or the 3 groups did. And we'll look in a minute why that might be so. And in terms of weight, actually there's a little increase in weight. Obviously people are a year older, but about a third to a quarter or half a kilogram extra in most arms. The Lancet still took it though. Okay. So a big question and a small word, why? Okay. The groups might not have been comparable at baseline. Maybe all the active people were in the control group and they were super keen and motivated to do even more activity, and all the people in the other group were just staying in their armchairs. This is called chance confounding bias. There might be a confounder, perhaps at baseline there were differences between the groups. But when we look at the groups across each row, you can see that those percentages in the first row and means in the second row and so on are very similar between the groups. And that's because we deliberately forced this to be the case. In the randomization, we used a method that allowed us to ensure that we would get comparable groups in terms of these selected variables. These variables covered a whole range of socio-demographic, physiological, psychological and behavior variables. Also, if we look at other variables, smoking, cholesterol, blood pressure, and the diabetes measure of control, HbA1c, these two were very comparable between the arms. So it wasn't that the groups weren't comparable at baseline. Was the study adequately sized? We needed 300, and we achieved 321. And the study set out to detect a 30-minute per day brisk walking on flat terrain distance, or equivalent of swimming or whatever activity that was measured objectively. We had the numbers there, so that couldn't be it. And there was about a 20-minute increase in physical activity per day in all 3 arms. So it shows that the measures had sensitivity to capture change as well. We perhaps might doubt the theory of planned behaviour. Maybe we shouldn't have built our intervention on this particular theory. And this led to a particular grant that Anne-Louise Kinmouth succeeded in getting from the MRC to enable several projects to be done. And one of those projects allowed me to spend half my time for about 3 years with David Spiegelhalter, a statistician in Cambridge, working on meta-analysis methods. And we had this idea that we could use these methods to pool all the information that there is around about the strength of the TPB. How strong are those arrows linking those 5 variables? Are they weak or strong? If we look at all the information from all of them, we perhaps might learn a lot more. So here's our theory of planned behaviour. We found 8 studies that have reported on the strength of these arrows. They reported on them in terms of correlation coefficients. And we had 8 particular meta-analysis methods. We had a bit of delight. We got into method development, and we got a bit away from perhaps the practical. We had our eye off the ball, perhaps. But this was very valuable because we found about 5 methods that were available and managed to develop them to make them up to 8. And so the big question would be, what is the strength of the 2 proximal links? The one from intention to future behaviour, is that strong or weak? And this one here, is that one strong or weak? Now, if they're both strong, then we built the study on the right theory. And by applying each of these 8 methods, they give a similar picture that the correlation for the lower link is around about 0.4, perhaps a bit less, and the one for intention, this one up here, is about just over 0.5. And so that information allowed us to see that perhaps this was quite a good theory on which to base the intervention. It does seem to hang together. So which of the 2 links is stronger? Quite a lot of the components of the intervention were based on the intention link, not the other one. And you might want to shut your eyes now because we're going to have a glimpse at the maths. It turned out that Pearson came up with a gruesome formula which allowed us to take the methods a bit further forward. This is all about comparing 2 links in the diagram. Is one bigger than the other? You need to also know the variability of each of those links and also how they covary. And this particular formula is all about the covariance. This is to make me look very important if I put in these pictures here, in the statistician's eyes. Okay. Which of these 2 links is the stronger? Well, we develop the method further to answer that particular question. So from each of these 8 alternative methods, one correlation was about 0.15 higher than the other, and it was the intention that was higher. So we did build the intervention, or Wendy and Stephen built the intervention on the right basis that the intervention link is stronger. So all of the methods, methodologically, all the methods indicate that intention is stronger than PBC link. And we can tell that because all those black squares are bigger than 0, for whatever method we look at. But if we want to generalize it to the broader population, some of the methods don't seem to think that this is the case and others do. How do we know that? Do they overlap this 0 line? And it turns out that the top 4 methods have got the precision wrong. If you ignore the variability, because there's a lot of variability between the studies, if you ignore that, you get 2 narrow confidence intervals. The first and the 4th method, too narrow. The second and the 3rd method are too wide, and that's because they've ignored the correlation between the links. We're correlating one link with another link, and they've got one variable in common. And so it's important also to take that into account. So it did turn out that we did need these more complex methods called multivariate meta-analysis, represented by the bottom 4 methods. And E to G were sort of classical methods and alternative methods that give pretty much the same answer and would indicate that there is an effect, that intention link is stronger, but the bottom method didn't, and this is what's called as a Bayesian method. And when we plug things into the formula, we need to account for the fact that there's a bit of variability in those estimates. Okay, I think you can unglimpse now. And so practically, were the theory of planned behaviour variables changed by the intervention? What happened in the trial? Well, we know that there was no significant effect on the physical activity. So the intervention didn't do what we wanted it to do. But there was some glimpse that it did work because it did alter intention at the 6-month point. People's intentions went up, but it didn't follow through to their behaviour. And if we look at their intention 12 months on, it faded. So some effect which faded. What about the theory itself? Was this borne out? Well, later on, Wendy and Susan, Mickey and Anne-Louise and Stephen produced a paper which showed that the correlation between the intention and behaviour links was actually quite weak in this study. So although the theory suggested, and the evidence from the 8 studies suggested you should design the study on this link, when it turned out it didn't materialise. So what are the other possibilities? People have said maybe the brief advice leaflet that everybody got, irrespective of arm, maybe that was itself a nice summary and very effective, and everybody changed their activity on the basis of that, receiving that leaflet. Or perhaps everybody was measured so much at the beginning and end with treadmills and wearing acti hearts, that all this measurement might have encouraged everyone who was on the edge of doing physical activity to actually do it. Maybe the measurement increased the activity in the advice group as well as the intervention group. And maybe we've got a keen minority of participants in the trial who've gone through this process to be recruited. Maybe they're very keen and will increase their activity whatever's given to them. Or perhaps the theory may not be applicable, and that might be suggested from that low correlation. So also maybe there's a low correspondence between the measures. Some of the measures were self-reported, but the physical activity was objectively reported. They may be capturing different elements of physical activity. Okay. So we have this intervention. What did it look like? Well, it had a number of components. You monitor what's going on, you goal review, you make action plans, you have goal setting, and you various other things. There turn out to be about 150 things involved within the intervention that are delivered over the 4 sessions. Quite a challenge, perhaps. And diabetes, could it be delivered is the big question. And Diabetes UK gave a grant to allow us to look at 10% of the sample, and it was quite interesting because only just under half of the components were delivered, and in the very first session, about 2/3 of the components were delivered, and as we go through the 4 sessions, lower and lower amounts are delivered. So it's quite a challenge to deliver these interventions. Nevertheless, the active bit that might be relevant for you might have been delivered to you. And if we look at the 4 intervention deliverers, the facilitators, some of them had participants where they were able to deliver a lot of the intervention and other facilitators a little. So that gave us a good insight into what might be going on. One thing that did happen in the trial was that people reported that their general health improved, both their physical health and their emotional health. And a lot of these points and whiskers at the bottom represent effects on the so-called SF36, self-reported health. And the 4 of the 8 components to do with emotional health were all what we call statistically significant. And of the physical ones, there was some evidence of that too, but only for 2 of them. And a PhD question for Neil Casey, who started a PhD at the end of the trial, was, are these effects genuine? Do they happen through the intervention? Is it self-report bias? People are trying to report in a pleasing way? Or could these have happened by chance? And he wanted to get further understanding on these effects. And so what we have is the group you're randomized through seems to influence these measures. If you get the intervention group, you're higher. If you get the control group, they seem to be lower. And the big interest is whether the effect occurred through a so-called mediator. So did it occur through what we thought it should occur through? So if people have more sessions than other people, we would expect the effect to be stronger. So we can decompose this effect into other effects. The effect that goes through the sessions, the mediator, and the bit left over. And what we'd like to see is that most of the effect goes through the mediator, and very little of it is left over. And that would confirm that the effect is perhaps a bit more genuine than we otherwise would have known. And a common method used is the Barron and Kenny method, called the causal steps method. Trouble with this method is that there could be a confounder out there. Perhaps busy people haven't got time to attend sessions, and also they haven't got time to try and do things that might improve their health. Whereas people who've got a lot of time, the opposite the case. So busyness could be a confounder and might induce an association between the mediator and the outcome. So another method by Rubin got around this by replacing what you actually observed, decomposing it into what you would have observed under the intervention and what you would have observed under the control. And that's quite an amazing thing, because you only supply one of these things, but we can actually use this method to estimate what your personal intervention effect might be by estimating these 2 quantities. We take the difference between them, and there's another letter, delta, that represents your personal effect. We can do this because we collect a lot of information at baseline. It's hopefully very predictive of these outcomes, what you might get in each group. And if we can find a good predictive B, then we get to get good information. Okay. So we replace all of these quantities by things that are predicted by baseline, and if it's predicted by baseline, we get around the confounder. And then we can see whether our personal intervention effects are associated with the number of sessions that we attended. And Neil's contribution was to take a J out of this equation. So it doesn't look very big, but it actually is quite a good thing to do, because if we've got 4 of these outcomes, these emotional scale outcomes, if we say that the effect can be combined across all 4 of them, we're putting more information in. Another way of thinking about it is that the Barron and Keddy method is a bit biased from the confounding bias, and we're shooting arrows over there. But the Rubin method does reduce the bias. We're around the bullseye now. On the other hand, the cost is that we lose precision. And, but if we use the method where we combine the 4 emotional outcomes together, we get bigger arrows, and we get not only the bias, but we get less imprecision. Okay. So we felt that the SF36 effects are probably more likely to be genuine, because they seem to be stronger when you're predicted to attend more sessions. So we've seen 2 kinds of variables: outcomes, which are the works variables. Does the intervention work? We can look at outcomes. How does the intervention work? We've got variables called mediators. These are other tools that we can use. We've also got biomarkers. So we answer questions with these, such as in cancer: who can we detect early with these variables? Who can we refer accurately from primary care to secondary care? And we have other questions we can answer. Who should we screen for diabetes? And certain variables can tell us who's most likely to have diabetes without knowing it. And in rheumatology and dermatology here at King's, whom should we stratify treatment by? And these are the sorts of questions I think of the future. So statistics in trials, making complexity work. How does that all come out of everything? Well, we started off with a lot of dimension problems, many food items, and we didn't know what we could do with them. I mean, a lot of complexity there. We could have observed complexity, these dietary items, or we could construct complexity in our intervention. We can do this through observational studies. We can do this through interventional trials. When we do it with observational studies, we're trying to make sense of complexity. But when we do it through interventional trials, often we're constructing complexity and trying to make complexity work. Dimension statistics has a lot to say in terms of dimension and trying to make things simpler. And often these are calibrated in terms of correlation. And this is something that has been around for quite a while and still very useful. We had correlation between the dietary items, and we had quite a lot of correlation also between those SF36 outcomes. And we can use methods that exploit all these connections. Statistics also tells us a bit about multiplicity. We may have mediators that can be usefully, we can judge mediators by combining lots of outcomes. We can stratify populations, try and find out how to personalise medicine. And at the moment, all that I've mentioned on this side would be about statistics. The thing that makes it medical is the bit in the bottom right-hand corner. For me, it's all about health. It's about the condition obesity, its consequences, diabetes, and its causes, lifestyle factors. So I hope you see that it's a wonderful job being a statistician. I can recommend it to you. There are a variety of conditions that you can learn about, a variety of questions that people come to you with, and a variety of methods that you can try and tweak. I have made a lot of friends. A lot of them are ologists, nutritional epidemiologists, psychologists, sociologists, epidemiologists, dermatologists, and rheumatologists. So that's good news. And I'd especially like to thank Janet Peacock, head of our statistics group, and the wider population of statistical colleagues from Southampton, Cambridge, and King's. And a special thank you to Teresa, my wife, and my children, Rebecca, Alex, and Nicola, sorry. looking at the picture, and the wider family as well, for their support and encouragement and love. And also, recently I haven't been around a lot because I've been developing this talk, so I'd like to say I'm sorry about that, but I hope you'll forgive me and leave you with a last cartoon. So, statistician on trial, making work complex. Okay, thank you very much.
So I now call upon Professor Charles Wolfe, Head of Division, to give the vote of thanks.
Thank you, Anne, and thank you all very much for coming this evening. I've got to give the vote of thanks, which is a great privilege to me. And I guess the only other analogy this week was the other inaugural, which was the Pope earlier this week. And I guess that went on for many, many hours. I didn't understand a word of it, so I'm not quite sure what the message was. But I sort of apologise for Kings in terms of the gowns were a bit more haute couture than we're wearing, and you all had to wear them as well. So I think we've heard a fantastic tour de force, a model of clarity, actually. There were 3 formulae, maybe 4, which for a statistical talk. And I think I was wondering whether Toby was talking as a mathematician, or as a medical statistician, or as a public health scientist, or as a health psychologist, or in fact as a clinical trials, either field worker, because you did do some field work, or as a coordinator. And I think you've actually assimilated all those skills, and that's really what makes Toby an ideal senior collaborator, because he's lived through all this, but you know, he's no hostage to fortune. I mean, he will pick the holes in anything and actually drill down onto it. So in terms of what we're looking at the ref at the moment, he certainly doesn't score very highly. Well, he scores highly, doesn't score anyone else highly, because he picks all the statistical holes. But because of that absolute breadth of expertise, that collaboration is really important. And he's certainly not the statistician that does postmortems for the clinicians' studies after they've done them. So, and I think it's great that he's maintained the links with Cambridge, and I see people who've moved to Cambridge and who are from Cambridge. But you can't randomise sheep, and I think it's really important to move from the Fenlands to come to South London, where you can do public health interventions in urban populations, and that's certainly the focus for King's Health Partners and KCL, and Toby's key to that with the statistical group here. So I think just before we finish, I tried to rake up some stories, couldn't find very much, except you must practice what you preach in the future, because I understand recently you went to a statistical conference in Bergen and you couldn't go to the mountain because you were going to do some meta-analysis or something. And but you said now you're a professor, you're not going to walk anywhere, so you took the cable car. So you've got to watch your scores and your points in the future. So thank you very much. And so what I'd like you to do is a round of applause to Toby for a wonderful lecture this evening.
So, ladies and gentlemen, I warmly invite you to a reception in the foyer.